So you ready for the quiz? So I'm giving you 2 minutes for that. Twenty seconds. What's your answer? Please put your answer, because I'm going to close it now. Okay, so let's try to look at the results. So gravimetric method in analytical can determine the quantity of analyzed based on the solid of mass. The answer there is true. And an assay is a chemical species whose amount is being determined in a quantitative analysis. So the answer there is what? Is it an assay? Okay, it's not an assay, it is an analyte. So this could be what? 20 points of your quiz for today that I'm going to give you by the end of class. And you have at least what? 20 minutes to answer that one and then submit it to me through Blackboard. Okay? Now, I can only include your score if you participate in the quiz, because being online doesn't mean you're participating. Right now, you are what? I think 12, but I only get 8 entries. No, I mean, when you say your name, okay, your screen name already is the one that I want, because some of you use other your first name, so sometimes I'm okay with Chem 221, but if it's a Chem 111 class, it's really hard. Okay, so we're going to do chapter 2. So we're going to do experimental error. So what do we include in this error? Okay, so today we're going to talk, or maybe have a review of these significant figures. We're going to discuss the different types of errors. We're going to discuss accuracy and precision. And last, we're going to discuss propagation of uncertainty. Okay? So in every measurement, there is always an associated errors. Okay? If you recall in our last meeting, these are the typical quantitative analysis. Okay? So we discussed, first thing that you're going to do, you select a method, you obtain a representative sample, and then you prepare your laboratory sample. You define the replicate samples, and then you dissolve the sample, you eliminate interference, and then you do the analysis. And once you get the analysis, you will have what? You calculate the results, and then you estimate the reliability of the results. Okay? Now, some errors are what we call small, but some errors are just, we could say, obviously wrong, like this one. The results are back from the lab. John Smith is pregnant. So what makes this interpretation absurd? Okay? Anyone? What makes this interpretation absurd? Okay? John Smith cannot be pregnant. Okay? So this is how you have to decide sometimes if the given results are what? Make sense or not at all. Like this one, right away you could say this is impossible. Now, what's the problem sometimes when you do analysis? Okay? And I think you can see it right now in our present state. So what's the problem that this country has at present? Anyone? What's the present problem?
Is it the interpretation of data?
It's the interpretation of data. Okay? So sometimes, if the result shows that it is against what you are saying, okay, sometimes you use power to just ignore the results. So what's the present problem right now? We have a big problem in public health. I don't know if you're going to agree with me. What is the public health that we have right now? Anyone? What's the public health that we have right now? That's why we're doing this way of teaching or learning right now. Okay? We have a problem of this. So what is happening right now? What's the problem that we have? Okay? Number one, the use of mass. Now, the question that you can ask, is there scientific evidence to back up, okay, the use of mass? Anyone? What can you say? Is there a scientific basis why the public should use mask? Or somebody just say it so everyone should do it? What can you say? Is there scientific basis why we need to use masks? So if you look at the news, okay, they said the reason why you should use mask is you prevent the spread of the virus. Okay, they were able to show some experiment that if you use mask, okay, you prevent the virus from spreading, because one way the virus that caused this COVID-19 is what? If they can only be transmitted from man to man or from person to person. And one way that they transmit is the spread of this virus by sneezing, by talking, by singing. Okay? And you could see that they have shown that if you use a mask, it prevents the spread not only of the virus but other microorganisms. And they were able to show, okay, in video how much particles transmitted when you sneeze or when you talk. Now, what else about the mask? After the mask, what else the problem that we have right now? Okay, the use of so-called what? Meds. How do you pronounce that? Hydroxy. What the hell is that? The one that is being what we called campaign by the president, hydroxyquinolone. Okay. So, is there empirical evidence that that use is effective? Or it's just, we could say, an anecdotal incident? Okay. And you might ask yourself, why is he keen on using this medicine? Why does he campaign that this medicine should be used to treat COVID-19? Okay. So the question that we have there are scientific evidence, but the problem is it's not enough, okay, to back up the use of this what we call hydroxyquinolone. It's not enough to give you enough evidence that it is effective. Now the problem is, okay, some people are campaigning for this use because they have their own personal interest. They have invested themselves in companies that produce this medicine. So that's what problem is science is being used, okay, for other non-scientific purposes. And that the problem with science, as you could see it right now, it's keep on changing because the knowledge of science just depends on the information that you got from different experiments. Okay, so one part that is really very important here is how are you going to interpret your result? Now, the best way to interpret this is in black and white. So what does it mean, black and white? Whatever the result, don't add any color to it. Okay, because right now, some people, okay, would use any information that they have or they got for their own personal purpose or for their own personal gain. Science should not be like that. Okay, it's black and white. If it's bad, then it's bad. If it's good, then it's good. You just need to implement policies that support whatever results that you get from this scientific experiment. Okay, so as I told you, the pregnancy test, it is called before the frog test or the rabbit test. But if you're going to look at the basis of the pregnancy test, what it is present there, that when you add a urine, you can determine if you're pregnant or not. Okay, so before, when you do the pregnancy test, you just look at the presence of a line. But right now, they get high tech. It can give you the word pregnant to say if you are pregnant or not. But if you're going to look at the basis of the pregnancy test, there's this thing called HCG. Okay, so it's the human chorionic gonadotropin or gonadotropin. So it's some sort of an antibody or enzyme that is present, okay, when one is pregnant. Okay. So usually only females has this chemical. Okay. But before, as I've told you, we went to the present pregnancy test. The way that they do it before is using the so-called rabbit test. So it was developed by Friedman, okay, in the University of Pennsylvania in 1931. So before they use rabbit, they use mice. Okay, and what they do here is they injected the urine to the ovary, and if they found the test is positive, so that female is pregnant. Okay. Now for the egg, the way that they use this pregnancy test, it induces the frog to lay eggs. Okay. Now the question: can a male get a positive results in the pregnancy test? The answer is yes, but that would be what? Bad news. If you use a kit, the pregnancy kit, okay, if you're male and you use it and it gets positive, that is bad news for you, because that means you have cancer. And I don't know if you have heard this cancer already, this part of the male. So that is the basis of this pregnancy test. And usually if you have a pregnancy test, it can give you right away the answer, right? What's the question that you have? Am I pregnant or not? So when you do the test, you will get this answer. Okay? So when we're doing, okay, any experiment, these are the things that you need to remember. Data of unknown quality are useless. So what does it mean? Okay. So whenever you do experiment, you have to make sure where are you going to get use this data, or why are you getting this data in the first place? Okay, because if you're just doing like an experiment and you get data with no purpose or objective on when to use it, so we could say they're useless. Okay, so there is no way to get or measure the true value of everything that you measure. So all experimental measurements contain experimental error, and this is where this term comes in. So there is always uncertainty in all measurements that we do. Okay? So it is necessary to determine the magnitude of the accuracy and reliability in your measurements. Then you can make a judgment about their usefulness. Okay, so whatever you do, you always put a room for uncertainty. Okay? So when you have this statement, we could just say there's no such thing as exact measurement. You will always have a degree of error in all measurements. And then another thing that you need to remember, it is necessary to determine the magnitude of the accuracy and reliability in your measurement. Okay, so what does it mean? Okay, what's the problem that we have with the COVID tests? Which is more reliable, the swab test or the blood test? Anyone?
The swab test.
The swab test. What's the selling point that they have for the blood test? The selling point that they have, as Abud said it, it's a rapid test. 15 minutes you get the results. But what's the problem? The problem is this, right? How reliable is the blood test?
50,
If you read some article,
50%.
they said it is what? 50%? Okay. So what does it mean? You get positive or negative? I think you heard the news about the Ohio governor who was supposed to meet the president. In the morning, he got what? A positive test or a positive results, but in the evening, he got a negative results. Two negative results. Okay? So whenever you're going to do the measurements, you have to have an idea how accurate it is. What is the reliability of the measurements? Okay? Because if it's not reliable in the first place, are you going to do the experiment? The answer is not, because you're just wasting your time. Okay? So if it's not reliable, why do it? Okay? So if it's not reliable, the next thing that you're going to do is find another test or another experiment that is more reliable. Okay? And then once you have that, you can make a judgment about their usefulness. So that's why I told you your results is useless if the way you do the experiments or the way that you do the analysis or measurement is not reliable. Okay? So these are stuff that you need to learn when you do data analysis or you do experimental analysis and you have data that you obtain from these different experiments. So the first thing that we can do is we could say, look at this look at the errors that we have here. So I just got it from the internet. Okay. So obviously these are not the one that you're selling, right? Are these onions? What are these? Is
Looks
it the
like
one that they're selling? This is?
it's corn.
Right? How about this? What's the problem here? It's from what? White Castle. What's the problem with this one?
It says 100% beef, but it's also said all white meat chicken.
They cannot decide whether it is beef or chicken. Okay? There are other stuff. This one, especially that the public school will open in a week. So what can you say about this bag? Okay. Is this Batman? Obviously, it starts with letter S, right? And Batman don't start with letter S. This one, I don't know if you notice it. So this one should be here. Now, these things happen, right? Because I don't think you can Photoshop pictures like this. Okay. But let's go on review of significant figures. So this is not new to you. Okay. So when we're talking about significant figures, this is the minimum number of digits to express or required to express a value, okay, in scientific notation without loss of accuracy. So if we're going to look at this, that's the minimum number of digits required to express a value in scientific notation without loss of accuracy. And they said there are two important quantities that we need to know: the number of significant figures and the place of the last significant digit. So example here, okay, how many significant figures does this number has? Anyone?
4.
Okay, so that has 4 significant figures. Okay, and the last digit here, we could say that's a significant number. So the last digit is in the hundreds. Okay, so what we're going to do is we're going to recall the different significant figures that you have. So the first thing that we need to do is about the zeros. How are zeros significant? So the first rule that we have for the significant figures is all non-zero figures are significant. And later on, I'm going to give you some sort of a sheet work, so you will see. Okay, you can determine how to look at what we call significant figures or not. One of your classmates cannot come in. Just try to answer. Okay. So what else do we know about the zero? So zero between two non-zero digits are significant. So these are what? These are the captive zero. So if you have it like this, okay, so we could say that zero there is significant. Another significant figures rule among zero is the so-called zeros to the right of non-zero digits and the decimal place are significant. So this is zero to the right of non-zero digits and the decimal place. So these are the trailing zeros. So example that I have there is this one. So the zero that being mentioned here is this and this. Okay, zeros to the right of non-zero digits. So this is a non-zero digits, okay, and you have a decimal place here. So this one, these zeros here, they are not significant. The only one that is significant is to the right of non-zero digits. So if you're going to ask how many significant figures you have here, so this is, we could say, significant figures. This one is also significant figures in terms of zero or significant. So how many significant figures do this number has? Anyone? Okay, so this has 4 significant figures. So what are those 4? 1, 2, 3, 4. So, question so far. Okay. So how about the other trailing zeros? Numbers ending with zeros to the left of the decimal point place and with no decimal point or additional zeros to the right of the decimal place. Okay? Can we consider them significant? The answer that you have there is it is insignificant, or in some books, indeterminate. So, not all trailing zeros are significant. Some trailing zeros are not. Okay, the example that we have here, okay, the sounds numbers can be expressed better using exponential is this one. 400 here is just what? One significant figures. And you could say this is trailing zeros. Now, if you want to express it into 2 or 3 significant figures, you have to use the scientific notation. So if really it has 2 significant figures, you're going to express 400s as this one. 4.0 times 10 to the 2. If you want to have it 3 significant figures, so you express it as this. Okay? So let's try to look at some of the examples. And maybe try to answer them yourself. Try to make it like a sit word. And then maybe I'll make a roll call. So try to answer them. So maybe I'll try to call people who are not really participating much. Avery, answer this one. How many significant figures that this has?
2.
Is it 2? Okay. Jennifer, what's your answer at least for this one?
2.
You said 2?
Yeah.
Bailey, how about here? 320.
2.
2. Okay. Kyle, how many significant figures is this last number here?
2.
I mean, this one? Your answer is 2 also?
No, 4.
Okay, 4. Okay, now let's try to answer them one by one if these significant figures are correct. Okay, 21.0, is it 2? So what type of 0 do we have here?
A trailing 0.
A trailing 0. Okay, so anything that is what? On the right side of a decimal place is significant or not?
Yes.
Yes. So is 2 the right answer here?
It's 3.
Okay, so if you're going to look at this is significant, significant, and also this one. So the right answer there is 3. Any question on that? Because you might have a multiple choice question about this in your exam and maybe in your quiz. Okay, this one. So you have here a trailing 0 and a leading 0. So any 0 on the left side of a non-zero number is a leading 0. And usually a leading 0 is not significant. So in this case, this is not significant, this is not significant. And then you may ask me, Professor, but you said anything after a decimal point is significant. Okay? But for 0, it is only significant if it follows a non-zero digit. Okay? But if the digit before the decimal is a 0, so that means it's not significant. And the 0 is also significant after a decimal if it's on the right side of a non-zero digit. So this is on the right side of a non-zero digit. This is on the right side of the non-zero digit. Thus making 2 here as your correct answer. 320. Okay? So the same thing that we have about the 0 being what? A trailing and before a decimal point. So this is an indeterminate. So this one will also has 2 significant figures. So if you want to make it 3 significant figures, what do you need to do? If you want to make that 3, you need to convert them into this. But this will only give you 2 significant figures. Let's go with the last one. Now, is this 0 significant? You have here what types of 0 are these? You have captive 0. And you have there a trailing 0. Now, captive 0, they're significant. trailing zero, since it's on the right side of a non-zero number that is also significant. So that makes it how many significant figures for this number?
5.
You have there 5 significant figures. Is that clear? Although we will have some operation later on. But right now it's just giving the number of significant figures in a given number. So what do you need to remember when you have these significant figures? Okay, you have to remember that the number of digits reported in the measurement reflect the accuracy of the measurement and the precision of the measuring device. All the figure knowns with certainty plus one extra figure are called significant figures. And in any calculation, the results are reported to the fewest significant figures for multiplication or division, or fewest decimal places for addition and subtraction. How are you going to record this measurement? So if you're going to look at this, you have there a 30. And then you have how many lines here? 1, 2. And then you have something between this and this. Okay, not really a 2. That's just a 0.2. Because I think what happened here is you will have it a reading like that. What's that? What does the 30.2 represent?
Like it's a certainty of the instrument that's used to measure. Precision. It's precise.
Yep. So you can say that at this measurement you're certain. Why? Because you have this calibration. The calibration of the measurement is 0.1 ml. So how do you define calibration? That's the smallest unit that you can measure based on the experiment. But as what I have said in the previous slide, all the figures known with certainty plus one extra figures. Okay, you need to add one extra figure. So that means if you're going to express the measurement here, it should have 4 significant figures. So what will be the last number? So you have to estimate between these two here. So you can write it like 30.24, 30.25, 30.26. But what information does it convey to you if you have a measurement like any of these? Anyone? What information does it tell you if you have data like this one? The information that it tells you is the last digit that you have there is an estimate or an uncertainty. Okay, so the last significant digit in a measured quantity has some associated uncertainty. Another information that it can tell you is you can determine the calibration curve. Okay? Even without looking at the instrument. So it's hard if you have an instrument like this or the one I think that I have here. So how are you going to do the reading here? Either you take it from this or this. But how are you going to get the reading here? So if you're going to get it from percent transmittance, so you have 50, you count 1, 2, 3, 4, 5, 6, 7, 8. So you're certain until that digit. Why? Because the calibration that you have here is just 1. But you can always what? Estimate the last digit that you have there. So it's between 8 and 9. So it is 0.5, 0.4, 0.3. Now, if you have that measurement, compare it to the other one, the absorbance. So how are you going to do the reading here? So you have here 0.2, and then you can count 1, 2, 3. And then since it's between 3 and 4, so you may put there what? 0.234, 0.233, because you could see here, oh, it's not half. Now, the question that I will ask you now is, which has more uncertainty? Is it the transmittance or the absorbance? Anyone? Which is more uncertain, or which has more uncertainty? Is it the transmittance or the absorbance?
The absorbance.
Is it the absorbance? Try to look at the number. So in transmittance, 58.3. So this is the one that is uncertain. In absorbance, it's 0.234. So which is the one that is uncertain? So which is a bigger number? The 0.4 or the 0.004 or the 0.3? That's how you answer the question, which has more uncertainty. Because this is a bigger number than this one. And this is what? If you look at the decimal place in the tens compared to this one, which is 1,000. So this has more uncertainty.
Wait, can you explain that one more time?
Hmm?
Can you explain that one more time, how that's more?
It has more uncertainty because between the two, you see the uncertainty is in the 0.3 or 0.4. Compare it to this one. So you can have what? 0.34, 0.33. So if you're going to look at the decimal points that you have here, here exactly it's in the tens, right? So if you're going to look at the percentage uncertainty there, a difference of 0.1 divided by, let's say, what's that, 58.3? compare it to a difference of 0.001 over 0.234. So which will give you a greater number. Try to do the calculation. I'm trying to look at my calculator. So if you're going to look at the difference, 58.4 minus, let's say 58.3, and then 0.234 minus 0.233. So which will give you a greater error. That's how they determine which has more uncertainty. Oh, there's something to do also here, how close the values are, or 58.3 and then 58.4 compared to this one. Okay. And it's really hard if you have, what type of instruments are these? An analog. Compare it to what? A digital. So in a digital, okay, it will give you right away the number that you have, although there's still what we call a representation that the last digit represents uncertainty. But you don't have to what we call use or think, is it 0.3 or is it close to 3 or 4? Because it cannot be 5, because a 5 should be in the middle. So what are you doing when you trying to do, is it a 0.4, 0.234 or 0.233? You're already doing an estimate on what value does this reading falls to. Okay? So these are just some stuff that you're going to do in reporting data following the significant figures rule. So you disregard all initial zeros. All remaining digits, including zeros between non-zero integers, are significant. Okay? So when you say initial zeros, these are the leading zeros. And these are the captive. And then addition and subtraction, the smallest number of digits to the right of the decimal sets the significance. Products and quotient, the smallest number of significant digits determines the significance. And then we have log and anti-log, because you're going to deal with pH. For log, keep as many digits to the right of the decimal as there are significant figures in the original number. For the anti-log, keep as many digits as there are digits to the right of the decimal point in the original number. We have example of this as we go on. Okay, so maybe I'll ask you to do it on your own. So we go to the mathematical operation. Addition and subtraction. So it says here, the place of the last significant digit is important, not the number of significant figures. So the place of the sum or difference is given by the least well-known place in numbers being added or subtracted. So how are you going to do this operation that you have here? So you have here 100 place and a 1 place. So what's the answer that we have here? So when you add them, this is your answer. Now, how would you express them in terms of the final answer? So you have here a hundreds and a ones place. So that means you have to round this up to 15. How about the answer here on the, trying to remove this thing. What's the answer here? 11.22 plus 3.8. Anyone?
15.0.
11.22 plus 3.8. So we can write the whole number first, or the whole answer. 15.02. So you have here 1 decimal, 2 decimal place, 1 decimal place. So the final answer should have 1 decimal place, or 1 digit after the decimal. Everybody got that? Let's try the next one, multiplication and division. So the number of significant figures is important. The number of significant figures in the quotient and the product is given by the smallest number of significant figures in numbers being multiplied or divided. So for instance, you have this number here. So you have what? 2 significant figures, 5 significant figures. So when you do the calculation there, you get this number. So how many significant figures the final answer has? 2 versus 5, 2 is less, so 2. So this one is still not exact, so you have to write it in scientific notation so that you can say that you really has 2 significant figures. Try to answer this one. What do you get?
5.1.
Huh? 5?
5.1.
5.1? So you will get there 5.08, right? But you have here 2 significant figures, 3 significant figures, so you have to express this in 2 significant figures. So you're going to express this as 5.1. Question. Before we go to the log, maybe you have not done this yet. Okay. So separate rules for the logarithms and the powers. So if you have a logarithms, the number of significant figures in the result to the right of the decimal point, that's the number of significant figures in the operand. Example, log 107. So 107 there, that's the operand. So that means you have three significant figures. So if you get the equivalent of that, you have to write your final answer in three significant figures. Now remember, where is the one that is significant? The one right side of the decimal place. So that means 1, 2, 3. This is not significant. So that's for the logarithm. Now how about for the powers? So in the powers, the number of significant figures in the result that is equal to the number of significant figures in the operand to the right of the decimal place. So if you're going to do it like this, 10 to the negative 11.6. So if you're going to do the operation, what's the value that you will get there? So you get there 2.51 times 10 to the negative 12. But the rule that you have there, okay, the number of significant figures is just equals to the one that you have there on the right side of the decimal point. So you can only express this into one significant figures. So you have to round out 2.51. So let's apply this in log 5.6 times 10 to the negative 9. How are you going to answer this? So if you get the answer for log 5.6 times 10 to the negative 9, you will get what? Negative 8 point. How will I write this sub here? I'm going to put you the number that we have. Are we going to put everything there? So how does my final answer looks like? Anyone?
Negative 8.3.
8 point?
3.
Is it 8.3?
Yeah. We rounded up.
Anyone? Any other answer?
Oh, sorry. It should be 8.25.
Okay, 8.25. So remember, you have here what? A log. So the significant figures in the result to the right of the decimal place, that's the significant figures in the operand.
So
So you
whatever.
only have here what?
So whatever.
1, 2, right? So where is the two significant figures here? Does it include the 8 or it don't include the 8? Right of the decimal place. So that means the 8 is not included. So the answer there is this one. Is that clear? Question. So question so far. Question. before we go to the errors. Before we continue on the errors. So let's go now with the errors. So they would say error is the difference between the measured value and the true value. Or you can put it like this. Now the question that you can ask there is, can we really determine the true value? Okay. So how do we know that we have an error if we don't know the true value? Okay. So today we're going to look at the types of errors. In most of the books, they just listed this one. Okay. But I want to include the third type of errors here, gross errors or blunders. So we have here the systematic or determinate errors. And then we have the random errors or indeterminate. So look at how this being the two main errors, determinate and indeterminate errors. Okay. So when we have a systematic error, so usually this is always off in one direction. Random or indeterminate, on the other hand, this is equally likely in any direction. Okay. Now, what I want to do is look at the errors that we have here. These are from the election 4 years ago. The three places where Hillary Clinton lost and the reason why Trump became the president. Look at the Michigan and Wisconsin counts here. So look at the difference of the values that we have there. What's the difference in Michigan? How many votes? 2,279,805 minus 2,268,193. So that's just around 11,000 votes. And the other one, 1,409,407 minus 1,382,210. So that's around what? 27,197 votes. Now, what do you think the third state? The third state is Pennsylvania. So 2,901,941 minus 2 million, not 2,000, okay? 844,705. 68,000 votes. So that's really close. But there's another election where much closer. This one. So when does this happen? 2000. Look at the margin of victory. Florida, 0.0092%. New Mexico, 0.06%. Wisconsin, 0.22%. Iowa, 0.31%. Oregon, 0.44%. And New Hampshire, 1.27%. What's the one that delayed the results from 2001? This one, Florida. And in my opinion, that should be question mark. Why? Who is the governor of Florida during that time? Isn't the governor of Florida also has a last name like one of the candidates? But for the sake of reunification, and Democrats are known for being soft, they just give way for the sake of the country. But if you're going to look at the small margin of error that happens here, that can happen also this year. Okay? And I don't know how the outcome will be this year. Will it be like 2000 results or worse? Okay? Now, let's go back with the determinate error. So as I've told you, determinate or errors always up in one direction. Okay? And there are three types of systematic or determinate error. It could be instrument, the method, or personal errors. That's why we could say that growths and blunders, it's really a determinate error. But I want to tell you what's really the difference of the growths and blunders compared to the personal errors. Okay? So if it's an instrument error, it has something to do with failure to calibrate, degradation of parts in the instrument, and power fluctuations. So what does this mean? Okay? If you have a pH meter, what is the first thing that you need to do to your pH meter before you use it? Anyone?
Calibrate it. Yeah.
You have to calibrate it. Okay? Because if you don't calibrate it, your pH may be too high or too low to the real pH. So if you don't calibrate it and you just want to get the relative pH, that would be fine. So either your pH is too high, but all your measurements will be giving you a higher pH. If it gives you an error of too low pH, then all the measurements that you have will have low pH. So if you're just going to look at the difference, that would be fine. If you're just looking at the relative pH of the different samples that you have. But if you want to get the true pH, then that's not right. So you have this what we call the systematic or determining errors. We observe it also. So I'm using this Raman, and every time I use the instrument, I have to run a standard solution. And the standard solution that I use is toluene. So toluene, whenever I run it, it has a peak around 1000 wave number. So what we're trying to do with the Raman. Raman is a vibrational method where you can determine any changes in the environment. And any small shift in the Raman spectra or in the peak in the Raman spectra is really a big deal for us. So what happened? After several years, we said, wow, there's a shift peak. So the one that we're looking around 1575, it shifted to around 1580. So we're so happy. And then my boss asked me, did you calibrate it just to make sure? And then I realized, oh yeah, I calibrated. And when I look at the calibration, the toluene also shift by 5 wave number. So that means the result that we have is useless. It doesn't show anything. Because if there's a shift in the standard by 5 wave number, So your sample will also have a shape of the same number. Okay? So there is already what we call an instrument error on that thing. Now, what's the other error that we have? Systematic error was what we call method error. So errors due to no ideal physical or chemical behavior. So it has something to do maybe on the completeness and speed of the reaction. So whenever you do experiment in your Gen Chem, whenever you measure the temperature, do you place your thermometer consistently in all runs? Let's say, do you hold it in such a way that the tip is in the middle of the solution, or you just put it all the way in the solution? Okay? If you do it consistently, then fine. But if you do it, one of your group mates is in the middle and one of you is in, just lay the thermometer on the beaker, then you have already there a method error. Okay. Another method error is the interfering side reaction. So you have to take into consideration some of the right side reaction that may happen, and it gives you error. Completeness and speed of the reaction. Are you swirling it in a consistent way, or you just swirl it so fast that the reaction happens so fast also? So what do you need to do there? You have to have consistency. You have to make sure that if you swirl it at a certain speed, the other run will also have the same speed. So you might swirl it like this, and one of you will swirl it like that. So there is already a method error there. Okay. Now, the last determinate error is the so-called personal errors. Okay. So how is the personal errors different from the gross or the blunders? When you do this color reaction, especially the one that would transition, let's say, from red to yellow, how do you say you're done? What's the color that will pass through if you transition from red to yellow? Anyone?
Orange?
Orange. Now the question is, how orange does your endpoint need to be before you call it, that's the endpoint that I have? Is it the first instances that the orange comes in? Or it is the last instances you see the orange and you're now going to the yellow color range? So how are you going to prevent them? So you have to be consistent with the endpoint color that you have. And I don't know if you experience it. Sometimes you think you're done. And then when you put your solution, what happened to your solution? If it's acid-base reaction using the phenolphthalein, you thought you get the permanent pink color, but after some time, what happened? It becomes what?
Turns back blue.
Is it blue? It becomes what we call colorless. Because in a phenolphthalein reaction, it's just either what? A colorless or a pink. So the first instance that the pink color appears, that's your endpoint. So sometimes you say, we're done. And then you put back the solution. And then after some time, it becomes colorless again. So those are personal errors. The one that, this is the root word that you have there. judgment. Okay? So when you have to do judgment, that is usually personal errors. And one error that can be a personal error is this one, biases. We can also have biases in science, in experiment, especially before you do the analysis, you already expect what the results will be. And the way you do it is you are focusing that you get that result, not awaiting what the real results will be. Did it happen to you that you have some biases already in the experiments that you're doing? If you already know what the result will be. So sometimes it's not good, okay? Because you already have some biases. Oh, the result should be like this. Because that's what you read in the thing. But usually I ask my students, especially those who are doing research with me, not all results that are reported are 100% true. And when that happens, all you need to do is you state the results from the previous study and state your own results. Right? You can say that I didn't get the expected results that was reported in the given paper. And if you're really sure that you might be the right one, what you need to do? You just have to repeat the experiment. That's why in sciences, you have to have an open mind. Although it was reported already that this is the results, sometimes that's not how it happened. Okay? And usually, what do they say? It doesn't mean that the first one who reported it is the one who do it correctly. Maybe in his or her excitement, he got the results, he published it right away. And then all of a sudden, when he tried to repeat the experiment, he cannot replicate his previous result or his or her previous result. So you always have an open mind when you do experiments. Okay? Now, what will be the effect of the systematic error? So it could be a constant error or a proportional errors. So if you have a constant error, so the error is of the same magnitude, regardless of the size of the measurement. This could be true when you have the solubility loss in gravimetric analysis or when you're reading a burette. So usually in reading a burette, what you have is the phalanx error. So it has something to do is how do you read the burette? So the best way to read the burette, so this is the burette, it should be eye level of whatever liquid you're reading, not lower or higher than you. Because if it's lower than higher, then you will have some error there. It's good if you consistently do it. If you do it like that, so your error is constant. If you do it like this, your error is constant. What makes it worse? Sometimes you do it at your eye level, sometimes lower than your eye level or higher than your eye level. Okay. And then number two, there's a proportional error. So the errors may increase or decrease with increasing or decreasing the sample size respectively. So in other words, the relative error remains constant. So either if you increase or decrease, but if you're going to look at the percentage of the increase and the decrease, okay, it increases because you use more sample. So it's still a constant error. So typically, it happens when you have a contaminant or interference in the sample. Okay? So how do you detect systematic errors? So let's say you become head of the laboratory. And the thing that you need to remember, when you're head, okay, so that means other people are doing the analysis for you. The first thing for you to have is don't trust the results. Okay? The same thing that I always do to my students. I don't trust the results, especially if they get it when they do it themselves. So how are you going to detect that there's a systematic error? So these are 4 ways to detect the what we call systematic errors. The first one is analysis of the standard samples. As I told you, systematic errors is a proportional or a constant error, so sometimes it's hard to detect these systematic errors, and you cannot analyze it statistically. So first thing that you can do is analysis of the standard sample. So what do you do there? You analyze samples of known concentration, such as the standard reference materials, okay? And your method should reproduce the known answer, okay? So what does it mean? You have a standard. So standard is, you know, the concentration of it. So when you analyze it to see if there's a systematic errors, then, okay, you will determine it. Or just like I told you, you calibrate it. So for me, how I know is my machine is working. If it's the portable Raman that we have there at Pace University, we use this acetaminophen, okay, or Tylenol. So I get the reading of the Tylenol and compare it to the reading that of the Tylenol and see if the peak match according to numbers. Another thing is blank determination. So if you observe a non-zero results, your method responds to more than you intend. Okay? Blank determination. So what does it mean? I have an experience of this when I was in grad school. So the lab is buying or purchasing a new instrument. And then what my boss told me is, Elmer sent them this material. And I have to ask him a follow-up question. Are you sure, Frank, that we're going to send this? And then he said, yes. And you know what's listed there? That he asked me to send to the company. It's listed there, pure deionized distilled water. And what do you think happened when we sent that material? Okay. Usually they will say, oh, there's a peak that we saw at this wave number. And they sent the identity of the material that was sent to us. And it's not deionized distilled water. They sent us some of the common dye that we use in the lab. So right away, they were already in doubt if they're indeed telling the truth. Okay? So these two, sometimes I tell it to my students, can you analyze this? And that's the way, okay, I can say if I can trust the student or not. If the student said, I don't get any reading, or the student said, I get a higher reading that is off the scale of the samples that we use. So there I can determine that the student is doing diligently the task given to him or her. Okay? Because what I usually do is maybe a standard or a blank. But you won't know it. I'm the only one who know what the sample is. So that's the second one that you need to do to detect systematic error. Now the third one is use different analytical methods. Now, there are many methods that you can develop. Some methods are already established. So if you want to determine if the method that you're being developed is correct, all you need to do is compare it with another method that is already established. So for instance, if you have silene, okay, you're trying to develop a method to detect the presence of silene in soil samples. So yes, you say you want to use Raman. So you want to make sure if that is correct, then you can use a GCMS method to detect if the results match. Okay, so that's the use of different analytical methods. Now the last one, round robin experiment. This is only useful if there are other laboratories that you can involve. Okay, or if you have it in your what we call lab, if you have different people. So what you're going to do here, you assign different people in a laboratory or several laboratories to analyze identical samples by the same or different methods. So what should be the results in the round robin experiment? Either they say they have the same results or at least close values that are close to one another. So question on that.
How often have you come across a standard that you had in the laboratory that wasn't up to its own standard? Like, I don't know, like it says it's 5% hydrochloric acid, but it turns out it's not.
So usually if it's a standard, they're usually accurate because you pay them for a much higher price compared to a typical reagent of the same chemical. So when you have a standard, when you purchase them, they usually give you an accurate results because you pay for them at a much higher price.
Yeah, but what if you have 20 people employed in a lab and they're not using the correct procedure to use it right? Has that ever happened?
Yeah, it happens. Usually when you want to determine how accurate your instrument is, you really have to use a standard. And you can use a standard that you prepare, or if you want the one that is 100%, you can purchase what we call a more expensive standard solution of whatever analyte that you want to determine. Okay, so usually what I do, I compare the standard that I just prepared in the lab with the standard that was purchased. And from there, I can determine the difference between the two as the error that is given by the instrument that I'm running. Question? Before we go on the other error. Okay, so let's continue with the other error, the random one. So from the word itself, random or indeterminate, okay? So these are errors that are caused by uncontrollable variables which cannot be defined. And the accumulated effect causes replicate measurements to fluctuate randomly around the mean. So it can be higher or lower than the true value. But what good with these random errors is it gives rise to this so-called normal or Gaussian curve. So if you're going to look at it like this, so this is a value that is too high. This is a value that is too low. So most of the time they are within the average. And the good thing with the random errors, you can always use statistics, which is the coverage of our next meeting, which we do asynchronously. So usually there's a statistical analysis that assumes a normal distribution. Okay, so where does this random error came out? So usually it arises from the effects of uncontrolled variable in measurements. So it can give you a positive or a negative error, and it's always present. That's the problem with the random error. It's always there, and you cannot correct it. Okay, sample of the random errors. We have this so-called electrical noise. So our instruments are run by what? Most instruments are run by electricity. So if there's fluctuation in your electricity, it can give what we call some erroneous noise in your signal. Okay. We can also have this in Raman. Our main problem is the presence of this cosmic rays. So it will always give us high peaks. So for us to determine if that peaks is due to our sample or due to the cosmic rays, all we need to do is just get several readings of our samples. And when we get the several readings, so that cosmic rays disappear. So if it just appear in one of the 5 readings, if you average them, you could say that that's not really true. Unlike the signal coming from the sample, whatever happened, you will always have that signal when you get the reading multiple times. Okay. Now, statistics is the one that can, we could say, use to fix the random errors. And the last type of errors that we have here, this is the gross error. So this is undetected mistakes that cause an experiment to be very much further from the mean, from the measurement than any other measurement or measured value. So if you have a gross errors, it can lead to an experimental value that can be discarded. And usually if you get these gross errors, you have the so-called outliers. So outliers are what? Values that are either too high or too low from a given set of values. And to determine if you have a gross errors or outliers, you can use statistics, whether you reject them or you retain the given value. Example of gross error are an obviously overrun endpoint titration. If you remember your general chemistry, so sometimes your phenolphthalein run is what? So dark. So that is already an overrun endpoint. What's the ideal endpoint? Usually a light pink color. That's the ideal one. Okay. And then you can also have an instrument breakdown, loss of a crucial sample, and the discovery that a pure reagent was actually contaminated. So those are the example of these gross errors. Okay. Now, the next slide that I have here, maybe you have encountered this already, accuracy and precision. So accuracy is a measure of how close a measured value is to a true value. Okay, so it describes how closer measured value to the true value. Precision, on the other hand, is a measure of the variability of the measured value. Precision describes reproducibility. So what does it mean? How close the measured values are close to one another. So ideally, we can compare accuracy and precision using the target here. So if this is the target, the bullseye that you have there, that is your, we could say, true value. So if you have measurements within the bullseye, the accuracy is high, so you could say it's accurate. And since the set of values that you have there are close to one another, you can also say it's precise. Ideally, this is what we want. Okay, a measurement that is accurate and at the same time precise. But there are some instances you can only have what? Precise measurement but not accurate. Such instance when the set of values that you have are close with one another, but they are way off the true value, just like the one that we have here. So this is precise, but not accurate. And the last one that we have here, poor precision. Accuracy is also not great. So as you could see here, the set of values are not close to one another, and they are not close also to each other. Okay. Now they said accuracy is affected by what? Systematic and random errors. But precision is usually affected by random errors. Between the two, which is easier to measure, accuracy or precision? Anyone? Which is easier to measure, accuracy or precision?
Accuracy?
Okay. Which is easier to measure? Is it accuracy or precision? Anyone? Want a roll call? In my opinion, okay, precision is easier to measure. Why? We don't know. As I've told you, we don't really know what's the true value unless it is given. So if we don't know the true value, it's so hard to measure accuracy. Precision, on the other hand, you just have a set of data. If they're close to one another, you can say they are precise. Accurate, well, if you know the true value, then you can measure accuracy. That's why between the two, I would say precision is easier to measure. Okay? So what I'm going to do, we'll take a 10-minute break, but I'm going to make the assignment available in the Blackboard. So you can start looking at the assignment, okay? So we will take a 10-minute break starting now, but you can start looking at the assignment.
Professor, it says that assignment.
Let us continue with the accuracy and precision discussion. So as I've told you, accuracy is affected by systematic and random errors, and precision, on the other hand, is affected mainly by random errors. And between the two, precision is easier to measure. Now let's look at this result from the Olympics. Okay, so this is, if I'm not mistaken, 2016 Olympics. So what can you say about the results here? Looking at the time. Okay, and if you're going to put the thing here, this is how it ended up. So you have 1 gold medalist and 3 silver medalists. How are we going to solve which one here first came second, third, and fourth? What's the practical solution? And if you have that power to do that, what are you going to do to determine which is second, which is third, and which is fourth? Because what you have here is just a first place and 3 second places. Okay? So how are you going to solve the problem here? Anyone? So how do we solve the problem here? Anyone? So the most practical way to solve the problem is you add maybe an additional timer here that is much, we could say, more accurate than the one that is presently being used. So the one that has 1,000 hen. And maybe by that time, you can really determine who's the second place, the third place, and the fourth place. Because all of them clock 51.14 seconds. So all of them get a silver medal. Okay? So the next thing that we're going to do in the chapter, and this is the last topic that we have in this chapter, is the so-called uncertainty. So as I have told you, every measurement has an uncertainty associated with it unless it is an exact counted integer such as the number of trials performed. And not just that, not just that measurement, you also have to take into consideration every calculated result also has an uncertainty related to the uncertainty in the measured data used to calculate it. So you already have uncertainty in your measurement. So if you do operations using those numbers from measurement, additional uncertainty will come in. Okay? So every calculated result, they also has uncertainty. So how do we look at these measures of uncertainty? So we could say explicitly, okay? So in this way, you're going to put the, what do you call this? Standard deviation. So measurement of carbon dioxide in the air gives you 389 plus or minus 3 ppm. So here, the uncertainty is described explicitly. So that means the true range or the true value should range from 386 to 392 ppm, some percent of the time. So where did you get this plus or minus 3 ppm? If you going to go on chapter 4, okay, you will see how statistic is used to determine the standard deviation. Or you can have an implicit uncertainty. Let's say the use of the significant figures. So 389 has a different meaning than 400 and 389.32. Okay, so that's the two measures of uncertainty. Now, how do we define absolute uncertainty, relative uncertainty, and percent relative uncertainty? So if you have absolute uncertainty, it expresses the margin of uncertainty associated with the measurement. the margin associated with the measurement. Okay, so when we say plus or minus 3 ppm, we could say that is absolute uncertainty. Okay. Now, relative uncertainty, on the other hand, it compared the size of the absolute uncertainty with the size associated with the measurement. So what happened? Okay. Relative uncertainty will say it's fixed, but the absolute uncertainty will go up or down based on the value of the measurement. Okay? And percent relative uncertainty, that's just 100 times the relative uncertainty. And the way that they look at it, this is what happened. If you increase the precision and they increase the trueness, okay? So increasing precision without increasing the trueness, you have to deals with the biases that you have. And then increasing the trueness without increasing the precision, you're increasing the error. But as both of them increase, okay, there's an increase in accuracy and a decrease in uncertainty. Now the question now is, how do we do this uncertainty calculation? Because now I just give you the sheet work, but how are we going to do this uncertainty calculation? So maybe I'm going to use a whiteboard here. Okay. So let's go with the addition and subtraction. So how do we determine the uncertainty? So for instance, the equation that they use here, okay, so uncertainty is just equals to the square root of the sum, or not the square, the squared of the sum of the different uncertainty. Example. So I have here 1.76 plus or minus 0.03, 1.89 plus or minus 0.02, and then 0.59 plus or minus 0.02. So let's say the way that we're going to do is we add this one and then we subtract that one. So we can get right away the value here, but not right away the uncertainty. So how are we going to solve here for the absolute uncertainty and the relative uncertainty? So maybe we should start doing them so that we'll be able to see how to solve uncertainty. So what's the value that we get here? So 1.76 plus 1.89 minus 0.59. So that is 3.06. So how do we get the uncertainty here? So we follow the formula that we have here. So E4, so that would be 0.03 squared plus 0.02 squared plus 0.02 squared. This will give you what? Anyone?
I got 0.04.
0.04. Did everybody got that?
So when doing the uncertainties, the plus or minus, we're still using significant figures, correct?
Yeah. We're still going to use it.
And the significant figures are relative to the uncertainties.
Do the operation here, you should be able to get 0.04. And you have to follow it based on the number that you have here. So you could write this as 3.06 plus or minus 0.04. Now, for the relative uncertainty, for this portion, okay, you can get the relative uncertainty as just 0.04 over 3.06 times 100. And this will give you what? 0.04 divided by 3.06, okay, times 100. So you get around 1.3 or 1%. So how are we going to write the relative uncertainty? So 3.06 plus or minus 1%. So those are the answers that you have there when you are asked to get the uncertainty for addition and subtraction. Analyze. So question, before we go with multiplication and division, okay, so now let's go with, I'm just going to end the share here. So let's go for another, what we call the thing. Just have to undo everything here. So let's go with multiplication, division. So let's say we have a given number like this, 1.76 plus or minus 0.03 times 1.89 plus or minus 0.02 over 0.59 plus minus 0.02. So in a multiplication and division, you can do it in terms of relative uncertainty. So we could say the percentage of your E4 is equals to the percentage of E1 squared plus percentage E2 squared plus percentage E3 squared. So try to do that thing. So if you're going to do the operation here, so that would be what? 1.76 times 1.89 divided by 0.59. So I have 5.6. And we're going to just put the next number there, okay, that would be around 5.64 because it's 5.637. So I put here a small number because the only one that is significant is 5.6. So what would be equals to in terms of the relative uncertainty and the absolute uncertainty? So how do we get the percent E1 squared here? So it's what? 0.03 divided by 1.76 times 100. So you have here what? 1.7. And then 0.02 divided by 1.89 times 100. So that's around what? 1.06 or 1.1. And then 0.02 divided by 0.59 times 100. So you have around 3.4 squared. So if you get that, I think I'm still missing another one. So you have to raise them to 1/2 or get the square root. So what do you get? What is the percent uncertainty that we have here?
I got 4%.
So you will get there 16, and then you get around 15 point something, which we round up to 16. And if you're going to get the percentage of that, you will have 4.0%. So right over here, you can write this as what? 5.6 plus or minus 4%. Now, if you want to get the absolute uncertainty, so all you need to do is what? The 4%. You're going to multiply it with 5.64. So you will get there around 5.6 plus or minus 0.2.
Professor, can you just actually, my mic, 1 second.
Yes? Yes, what do you want to? Oh, where did I get the 0.2? So I multiply the 4% with 5.64 to get the absolute. So 4%, that's 4 divided by 100 times 5.64. So you will get around 0.2256, but you only have 1 decimal place. So you just use 0.2. So question, now what if you mix them? What happened when you mix them? Then you have to follow, you have to do it one by one. Okay? So for instance, I'm going to give you a number here where I'm going to mix the operation. So I would have 1.76 plus or minus, or maybe I'm going to use the same thing as this one. But I'm going to use 59 here. So plus minus 0.02. And then I'm going to divide it with 1.89. So how am I going to solve this one? Then you have to do it step by step. So maybe the next thing that I'm going to do is maybe I have to get this numerator calculation first. So if I have that, that would be 1.76 minus 0.59. So that will give me 1.17 and plus or minus. So I'm going to use the 0.03 squared plus 0.02 squared to get me the initial uncertainty here. So that would be equals to what? 0.03 squared plus 0.02 squared. Get the square root of that, I'll have around 0.036. So I can write the whole thing because it's not the final answer yet. Because that number, I'm going to use it to divide with 1.89 plus minus 0.02. So if I have that, 1.17 divided by 1.89, so I have here now 0.619. So I'm not what we call rounding them up yet. Okay, so what will I do? 0.619 plus or minus, what will this be? So I can use the percentage that I have here. Okay, so the way that you do percentage E, so I could use the square root, and then I could use here the 0.036 over 1.17 times 100 squared plus 0.02 over 1.89 times 100 squared. What would be the number that I will get from here? So 0.036 divided by 1.17 times 100, and then I get the square root of that plus 0.02 So I get 9.47, get the square root of that, I get around 3 point something. What did you get? If I want to continue this item here, I could make it 3.08, and then this one is 1.06 squared. So what's the percentage uncertainty we'll get there? Anyone?
I got my final percentage as 3%.
3%. So around what? 3 point?
I got 3.254, but I rounded it.
Okay,
Yeah.
so around maybe like this one, 3.254, so around 2. So if we're going to follow it, if we round this up, okay, so as you could see here, if we follow this one, 3, 3, 2, so we might round this up as 0.62 plus or minus 3%. And then in terms of absolute, so you can use the whole 3.25 divided by 100 times 0.62. So you will get around what? What's the absolute uncertainty? Anyone? What's the 3% of 0.62?
0.02.
0.02. So that is your absolute uncertainty. So the next slide that I have there is that will be the assignment that you're going to do. And most likely your next quiz has something to do with uncertainty. So analyze before I go back to my PowerPoint slide. And then we talk about others' uncertainty. Question? So this one, usually I give it as a sit work, but I leave it up to you. Most likely this will be the assignment that I'm going to give you. So let's talk about the other uncertainty, like propagation of uncertainty. What does it mean? Okay. So it refers to the situations when one or more variables are measured in order to calculate another variable. Example is the volume of liquid delivered by a burette. So there are uncertainty on that. So for instance, you usually record your initial volume and usually it's 0. Okay? And then you deliver a liquid, you will have your final volume. So that in case the volume of your burette is based on the difference between the final volume and the initial volume. Now, what does it mean? Okay, so there is uncertainty in the volume of your burette, and it can be calculated by looking at the uncertainty in the initial and the final volume, or maybe by making multiple reading to get the multiple values of the volume of your burette. And the calculation that we can have here, if we have a volume of a rectangular solid, so we have what? Volume is just equals to length times height times width. And if we have to calculate it with respect to the density of a liquid, we have to take into consideration the mass of the liquid. So how are we going to do this propagation of uncertainty? How do we solve this problem? So the volume delivered by a burette is the difference between the final and the initial reading. If the uncertainty in each reading is plus minus 0.02 ml, what is the uncertainty of the volume delivered? Suppose that the initial reading is 0.05 and the final reading is 17.88.02. So how do we solve this problem? The same thing as we did earlier. So this is what? Subtraction. So 1788, 17.88 minus 0.05. What do you get there? 17.83. Now the question is, what is the uncertainty here? So what do we do? Okay, so we have uncertainty here. So this is just equals to the square root of 0.02 squared plus 0.02 squared. And that is equals to what? 0.02 squared plus 0.02 squared. You get the square root. So that is 0.03. So the way that you're going to put it is like this. Were you able to get it? Were you able to get the 0.03? Now, how about this one? How are we going to solve this problem? Assigning uncertainty in experimental data and calculated results. So there are three ways in solving this problem. Okay. So a 0.218 gram, 1 gram of sample of KHP was titrated with 8.98 ml of NaOH. So you are asked, what is the molarity of NaOH? So how can we solve this problem? So maybe the first way to solve the problem is we use any associated uncertainty, or we do it the typical way. Okay, so we get the corresponding moles of your KHP, and then from that we'll be able to get the molarity of your NaH. So how do we get the mole of KHP? So you have 0.2181 grams divided by the molar mass of KHP. We could say 204.233 grams per mole. And this will give us what? Point 2181 divided by 204.233. So we can put it like this. 1.0679 times 10 to the negative 3 moles. And then that's not the final answer yet, because we just get here the number of moles. So once we get the number of moles of the KHP, that is also the number of moles of your NaOH, because they have a 1:1 mole ratio, right? Are you still with me?
Yes.
But this is also the same number of moles with your NaOH. So we're going to use that number to get the molarity. How? We have the corresponding volume of your NaOH. So we could just set 8.98, convert it to liter. So right away, we have what? 1.0679 exponent negative 3 divided by 8.98 exponent negative 3. So you have here 0.11892. Or if we're going to simplify this, we need to write it as what?
We have to write it as 3 significant figures. 0.
That's 3. Yep, that's 3. Yep,
0.119.
Yep. Thank you. Now, as you could see here, the KHP has 4 significant figures. Okay. Now, the KHP should have, the moles of the KHP should have 4 significant figures. Okay? Now, the NaOH, the one that we have here, we have 3 significant figures for the what we call NaOH. So that is the limiting value that we have here. Okay? So try to monitor that thing and then try to see if it's the right one, because that's the simplest one. I just need to take a call. Now, how do we apply uncertainty here? So the one that we did right now, that's the simplest one. We uses the implicit uncertainty in each measurement. So significant figures to determine, okay, what's the final answer, depending on the number of significant figures that we have. So we just follow the rules of the significant figures. Okay. Now the second one, you uses uncertainty and precision of each measurement arising from the limitations of the devices and the contribution of each uncertainty to the final result that is calculated. Now that is useful if you have a single measurement, just like what we have. Or do we have a single measurement here? Because if you're going to look at here, you have at least what?
We have 2.
2 measurements. Okay, so that would be a little bit tedious. Okay, so the way that you're going to do here is from the time that you get the moles of the KHP until you get the molarity, so you have to do this uncertainty that you have. So what does it mean? So when you get the mole of the KHP, there is a corresponding uncertainty there that you have. So how do you do the calculation there? So you have there the uncertainty of the moles over whatever moles that you have. Okay, so that's a little bit tedious. And if you're going to what we call work on it, okay, you will get a value that is, we could say, around 0.1189 plus or minus 0.0004. So that is following the second rule, wherein you have to take into consideration all the uncertainty. Now, as you could say, I need to use the whole decimal places here because of the uncertainty that I have. Okay, because here, if I just follow the significant figures rule, I can just say 0.119. But if I have to look at the uncertainty propagation, I end up using, instead of 3, 4 significant figures. Why? Because of the uncertainty. I didn't show you how to do it, but you will end up with this one. Because I'm trying just to tell you, if you have a set of data, there are many ways to express the calculated result. And in each of them, there are uncertainty that is assigned. Okay? Now, what do you think is the third one? So this is the first one. This is the second one. So the third one is what you do next chapter, the use of statistics. And we're not going to do it here. But that is another what we call tedious calculation. Okay? So the first one, use of significant figures. The second one, use of uncertainty. The third one, use of statistics. Now, what can you say? Significant figures, you end up with this one. Uncertainty, you end up with a more accurate reading. In statistics, then you will have the range that would be close to what the uncertainty gave us. Okay? So maybe right now you are in this level, but you are now going to this level wherein, oh, I can express more. Okay? The information that I have from the given data, and I can even include the uncertainty that I have. So question. The last part that I have here, what can you say about this? So what is wrong with this one? What is wrong with this slide? The photo in the slide. Oop, I think I ended up. Is that this one? So this is what? The pathway of a hurricane. And I think that's Dorian. That's from last year. Okay. So why do you have to put something like this? Because the way that they're going to what we could simulate this one is maybe like that one. Or maybe when they got smoke. So this is what we could say, using data for personal purposes. Okay? So question about chapter 2. And have you started doing the quiz? I also sent this morning an information how you're going to submit it. So where you get it, that's also where you're going to deposit the document related to the quiz. So solve it in a piece of paper, take a photo of that, and then convert that into PDF and then sign it, and what we call submit it. Question? Anyone? You can show your face now.
For the quiz, I actually typed in Word document and saved as PDF file. Is that gonna be okay for you, or I have to?
It's okay. Okay, but I would prefer at least write up just in case.
Right. Okay. I'll redo
I
it.
also have a hard time reading if it's typewritten.
Okay. I'll redo that.
Professor, I wrote it on my tablet. Can I just? That's fine,
Yeah.
right?
Yeah.
Okay.
As long as you can send a document copy, you can submit a document copy of that.
Okay.
Because I'm giving you the remaining more than 10 minutes to answer that. So what happens, I forgot to post an assignment. Supposedly every meeting we have an assignment. So that means next week you were going to submit 2 assignments. Okay. So I already posted assignment 1. Maybe tonight I'm going to post assignment 2. And next week we're going to meet asynchronously. So I'm just going to post a recording of the lecture for next week. So question. So this week we're going to do experiment 2, and we're going to do it in online mode. So some of you has already emailed to me who your partner will be and who will be doing the experiment. Now I only know 3 out of 4 who will opt to do online. Okay? So I need to know who's the one that participated in the survey last week that unfortunately I put as anonymous, so I was not able to determine the student who's going to perform online or will not be able to do the in-person one. So I already know 3 of them because supposedly there's only 3, but there's an additional one. So that makes the 3rd person. So I'm still looking for the 4th person. Okay. And maybe by Wednesday, we will know who will be there next Wednesday. The first 6 students to do the in-person lab. And I also want you to submit or do the discussion forum, the question that I have posted there, and the lab safety. There's a lab safety video that is already posted, and then there's a quiz that goes with it, okay, in the assessment. And then I'm going to upload also the document that you need to sign, print, and then submit to me during the in-person class. For those who are not in person, you sign it and then submit to me online, the document. I have not posted that document yet, but I will post it by Wednesday. So question? Anyone? So do the quiz. The quiz you need to submit by 12. Okay? So if none, see you Wednesday.
See you on Wednesday.
Okay.
Bye. See you on Wednesday.
Okay.